So today we'll be solving this Leetcode problem. Minimum operations to convert all elements to 0. It is number 3542 and it is marked medium, and the problem statement says that you are given an array nums of size n consisting of non-negative integers. Your task is to apply some operations on the array so that all elements become 0. In one operation, you can select subarray I to j and set all occurrences of the minimum non-negative integer and that subarray to 0. Return the minimum number of operations required to make all the elements in the array 0. So for example, if the nums are given here are 1, 2, 1, 2, 1, 2. So in one operation, you can select any size subarray and turn the minimum element in that subarray to 0. So that we can do, and we need to return the minimum number of operations that will be needed. So for example, in this nums array, the minimum element is 1 if we take the complete subarray, and then if we turn this 2 into 0, so this becomes 0, 2, then 0, then 2 again, then 0, then 2. And again, if again we need to turn these 2 into 0, so since we cannot take the bigger any subarray which is larger than 1, because that will include 0, and then minimum, in that case minimum will become 0, and using 0 we cannot, because minimum element is 0, so we cannot turn these 2 into 0 itself, because the problem statement says that we can only turn the minimum value into 0. So in this case, each of the 2 here should be turned into 0 separately. So this is the core intuition of solving this problem, because after turning any of them into 0, it basically creates a segment of numbers, or you can say sort of like island of numbers, right? Which basically those islands need to be solved separately. So here in this case, if we remove these zeros, we'll see that we'll at the end we end up with 3 islands, right? So these 3 islands needs to be solved, and since these are not connected, so again turning all of them will require one operation each. So at the end we'll have a total of 4 operations. 1 for turning all of the ones to 0, plus 3 operations will be needed for turning each of the 2's into 0s, right? So total 4 operations will be needed in this case. Now if we come into this case, this example over here if you see the and it is always wise to take the, for the first case, if we take the minimum value itself and take all the subarray where as a large subarray which contains the minimum value as 2 itself, it's always best way to take that option. Since if we take this subarray, for example over here, even if we take this complete subarray or the subarray starting from here to here, it still has the minimum element as 2. So it doesn't matter if we take the complete array or this array. So we will end up with the same resultant array, right? After turning the minimum element to 0. So we'll have 5, 0, then 3, then 3, then 0, then we have 3, 7, and then 3, then 0, then 5. And then if we ignore these zeros, so zeros are basically splitting the array into 2 parts and creating sort of like islands over here, right? So if you see 7 3 and these will be included. Yeah, so it is creating these sort of islands of numbers, right? So let me remove this over here as well. Yeah, so it is creating these islands, and then these islands needs to be solved. So if we take this middle island for example over here, so which is 373, and in this case the minimum element is 3 itself. So if we change all these 3 into 0, again it is creating an island of number 7. So what the gist that we get over here is like each the element with the largest value is being removed at the end, and all these minimum value in between of these numbers connect all those two islands, right? So this intuition basically gives me towards a solution of using union find algorithm for that. Even though this problem basically can be solved with monotonic stack in better time complexity in order of n, and there are various other solutions present already, which is covered by other people. But I wanted to cover this solution in a different way, where we'll be solving this problem into big of n log n time. I know it is a bit worse than order of n time using monotonic stack, but it is a bit different solution. So yeah. So if we consider this example over here, what if uh, the thought process that I had to solve this is like, why don't we go in the opposite way? What if we start with the largest value and then keep on adding the smallest value together and keep connecting the islands, right? So if we see like what if so in the solution that I'm thinking of is like I'm trying to recreate this original array from the numbers I have by adding one by one to the existing island of numbers we have. So initially, so we can sort of like say something like we'll create we'll have a map of all these numbers and its indices, right? So let's say we have number 7 and its index is 0 1 2 3 4 5 6. So its index is 6, and then we also have uh, less than 7, it is 5, so it is indexed at 0. Then we have uh, 6 7 8 9, so it is indexed at 9 as well. And then we have 3, so 3 is indexed at 2 3 5 and 7, 2 3 5 and 7, and 2 is indexed at 1 4 and 5 6 7 8, 1 4 8. So what if let me do this. Yeah. So what if we process all of these numbers one by one and we keep adding into our array, right? So basically what we'll do is we'll have an array. So let me draw this 1 second. So here, so let's take this. So we have index 0, we have 1, and then we have 2 as well. Okay. We have 3, we have 4, we have 5, 6, 7, 8, then 9. Okay. So what this is going to help us do is like we can keep clubbing all these values once we go one by one. So let's suppose 7 comes in and it is indexed at 6, right? So we'll check if there is any element which are neighboring to this 6 and if there is any island already existing. If there are any, then we unify them and we connect all these islands together, and then at the end we check if the this number, this this index or any other index, if there are any multiple, so we'll see that, but if there are any other element are in are neighbor to 8, which is of 7 which has value 7, are any neighbor to it, if they are part of any other the island, then we don't increment the result counter because we don't need any operation to change it again, because that must have been removed altogether, right? So if we see this 7, so we add we mark it as true because we have already visited it. So one island is already existing now. So in this case, uh, now we process the number 5. Then we see that if at index 0, is there any element in either in the left or on the right is present or not, right? So if there is any, we could have unified them, right? Connected all those two islands. So if there isn't any, so we just don't do anything. But in case of 9, if you see also there is none element present on the left or none in the right. So we just skip it. But in case of let's 3, we'll see why. Okay, so in case of 3, we have index 2. In with respect to 2, there is no island present on left at 1 or on the 3 as well. So we just keep it true over here because we have found one island, and then we have 3 indexed at 3. So in case of 3, we see that there is one island we have already found, right? At 2. So we unified 2 and 3 together, right? And in case of 5, we encounter 5 over here. So while unifying, after when we have unified it, right, we also make a check if if either it is a first element or the subsequent indices of a particular value are part of the same set or not, same island or not. If they are part of the same island, we don't count it again, right? We don't need to perform the same operation again because they all can be part of the same subarray and they can be turned into 0 at once, right? So that's why I have I need I also need to make a check if they are part of the same set or not. How can we do that? We can do that by using this island indexes, right? We can try to run the union find algorithm. We can get the parent of both the indices, the previous one and the current one, and if they are part of the same island, we don't we don't perform the operation again. Okay. Uh, and so in our case, for in the value 3, we'll be adding only the operation once when we are adding for the 2, because there are no any island present either in the left or on the right, and it doesn't have any other value which is present in those two islands, right? So we add operation result 1 again. So in our case, let's also keep track of the number of operations we have performed. So for the 7, we have performed once. For 5, we have performed twice because there were no islands present for both these indices. And in case of 3, we performed only once for the 2, but for 3 we didn't perform any operation because for the 3 there is one island present and the index previous to 3 is 2 and they are connected because we are checking this condition if they are part of the same island or not after unifying it, after connecting those two islands. So since they are part of the same island, we didn't include the operation again. Then we came to 5, then we checked if there are any other neighboring uh, island or not. Since there are none, so we need to add it again. So here we need to add again, right? So let's make it as true as well. And then we come to index 7. Okay. 7. Okay. I think a mistake over here. Okay, so it was at 6. My bad. Okay. So when we come at index 7, so we see on the left there is one island present, but on the right uh, there are not any. So we'll check if there is any element which is part of this left island, right? And which is has just previous index. So we'll check if uh, uh, so since there are one island present in the left, so for index 7, we'll unify this with the previous index, and we'll check if the previous index and the current index are part of the same island. If they are, so we then in that case we don't need to add. So in as you can see at index 7, after clubbing it, there is 5 which is part of the same island. So we don't add it again. Okay. Next, if you see for the 2, so we add 1 again, 1 over here. So for 1, even though there are islands present on the left or on the right, we unify it. That's fine. But since there are no element present previous to this 1, it means that we are adding 2 for the first time. So we definitely have to perform the operation over here. So we added 1 again, and then we check for 4. So for 4, there is also island present on the left and also on the right. So we unify both the islands. So since if you see, we are connecting those two islands, and after connecting this part, this whole thing becomes one island. And this island contains the index 1 as well. And 1 has the value 2. It means that we should not perform the same operation again, right? Now coming to 8, 8 is also you connecting these two islands, right? The island with the parent is 9 and this island is some other parent, right? So we will connect it, but after connecting it, we can see that this becomes the complete one island, but it also contains the index 4, which is the previous index to 8. It means that 2 must have already been part of this current running this subarray, right? So we don't need to perform this operation again. So at the end, we'll get the minimum number of operation as 6. 2 plus 1, 3 plus 3, 6. Only 6 operation is required. We can also validate this over here. So in one operation, we turned all these 2's into zeros, right? So, and then we were left with these numbers only. So let's count the result over here as well. So result was 1 for converting all these 2's into zeros. Then let's also add 2's in between to distinguish. And then 0. Yeah. So if you see, now we need to remove these 3's as well, right? So for changing these, we'll need one operation for this, one operation for this. So in two operation, we can change all of the 3's into zeros. So then it will become 5, 0, 0, 0, 5, 0, 0, and 0, yeah, and then 0 again, then 7, then 0, then 0, then 5. Now we are left with number 5, but we cannot take this complete subarray because in between comes the minimum element zeros, right? So we need two operations to turn this 5 and this 5 into 0. So we'll need two operations for this. So we can convert this into zeros, right? And then at the end, we'll also left with other zeros. So now we can see that now we are left with only one element, which is this 7, and we'll need this one subarray for that and only one operation for that to change it, right? So we'll need one operation for that. So we can see like it matches with the result. So total 6 operations is needed. Now talking about the implementations. So let me write that. Yeah. So what I'm doing is I'm maintaining a union find algorithm for that. Using a union find algorithm, I'm clubbing all these islands together. Okay. And I'm maintaining size based on the size. I'm clubbing, deciding who will be the parent of who, and then at the end, I'm on the descending order. I'm processing all these indices one by one. So if I talk, if I let me write it down the implementation over here, and then we can explain. Yeah, so let me first explain the union find algorithm over here. I'm using this parent to maintain the parent of each of the node and size for each of the size. And this is basically all the union algorithm and the find parent algorithm for that. And here this function is basically telling us that if the two nodes are part of the same set or not. It means that when we were talking about these indices for 4 and 8, the previous index, if they are part of the same island or not, right? To decide if the subsequent operation is needed or not, right? So this is the main function, which is like basically initializing the parent array and the size array, and this clubbed is basically used to see if there is any island present on the left or on the right or not. Here I'm using the sorted map for that, and for each of the element I'm initializing the parent for each of the element as itself and the size as 1, and then I'm putting in the map uh, its index for each of the element. Then I'm taking out the key set in descending order to process them in descending way. First the 7, then 5, then 3, then 2, right? Then for each of the index, I'm taking out the index itself, and then I'm comparing if if there is any uh, island present in the left or not. If there is any present, I'll unify it with the current index. If there is any element present on the right or not, that also I'm checking, and I'm unifying the right island. Once unification of both islands are done, then I'm checking if either this one was the first element to encounter, first element of the same value is encountered. If it is so, then we definitely need to perform one operation for that. If it is not, it means that if that element is already present in that some same subarray or the same same island, it means that we uh, we don't need to perform. Since I've applied a not over here, it means if they are not in the same island, then we definitely need to perform the operation again. So either of these cases, we need to add one more operation, and I'm then marking the current index as that this is part of there is one island exist in this particular index, right? And at the end, that will be giving us the result. Okay. So here is a solution to find the parent and the unification. Based on the size, I'm deciding who will be parent during the unification after comparing if they are not a part of the same island. Hope this is clear now. Thank you.